Complicated. Seriously massive objects warp the fabric of space. The heavier the star, that is, the greater its mass, the greater the distortion. So light, which would otherwise travel in a straight path, gets bent. If a star of any given mass shrinks sufficiently, its density increases until its local distortion of space is infinite. That's a black hole. A border develops separating the black hole from the space around it. Once this border has been crossed, going into the black hole, even light cannot escape. Border diameter is determined by the weight of the compressed mass. A hole with the same mass as Earth would be merely 2 centimeters across, something the mass of the Sun, 6 kilometers. That's considered the size of the black hole. Black holes are created the instant stars die. Let's say a star 20 or more times larger than our Sun reaches the end of its life and explodes. The star's own gravity then causes its remaining core to implode infinitely, becoming a purely gravitational force. When a black hole is born like this from the death of a star, its diameter is 50 kilometers at most. But one can find black holes of truly monstrous proportions, over 10 billion kilometers in diameter. Andrea Ghez is an expert on this invisible phenomenon of the black hole. It was when she saw the Apollo moon landing on TV that her interest in space was awakened.
My biggest objective in life when I was very young was to become a ballerina. So I think I see things spinning in space now as opposed to myself. But yeah, your path the path was unclear. And today I view doing astronomy and studying the black hole as putting together one big puzzle.
Donald Lyndon Bell predicted that a supermassive black hole lurks at the heart of every galaxy. Andrea Ghez tried to find such a black hole in our own Milky Way galaxy.
Or actually, the first thing that we're trying to do is watch how stars move. That's the key to finding that there's a black hole. And the way you do this is by pointing your telescope at the center of the galaxy and using a technique that allows you to see the stars around the black hole. So here's the black hole. And what you want to do is we want to be able to see a star. You want to be able to see a star make a complete orbit around the center.
Ghez followed the movements of the stars for years, plotting their trajectories. If they were in fact orbiting some unseen object, then that would be proof of a black hole. The center of the Milky Way, however, is 26,000 light-years from Earth. Ascertaining the movements of stars around a point so far off in space is no easy matter. Mauna Kea, Hawaii, home to several giant telescopes. Ghez used one of the observatories on this summit, the Keck Observatory. The Keck has 2 of the largest telescopes in the world, with primary mirrors that are 10 meters in diameter. Gez's observations here began in 1995. But Gez and her team were not the only ones searching for a supermassive black hole in the center of our galaxy. A European team based in the heart of Germany had also been hunting the same monster. The leader of these star trackers is Stefan Gelessen.
They have a 10-meter telescope. We have an 8-meter telescope. So our telescope is a bit smaller. However, we are on the southern hemisphere, where the galactic center is visible for more hours. So we can observe from February to October.
The European team conducts its observations at the Paranal Observatory in Chile. The VLT array there comprises 4 8.2-meter telescopes. But even with such advanced technology, success is elusive. The problem is Earth's atmosphere. Atmospheric fluctuations blur the stars. April 2002, the European team installs epoch-making new equipment. From the VLT at Paranal, they shoot laser beams into the night sky to measure and adjust for those atmospheric fluctuations. Their special equipment succeeds in doing just that. The new method is called adaptive optics. It brings the stars into focus. Corrected for atmospheric fluctuations, the stars shine much more clearly. Gez, who did not yet have adaptive optics, was at a disadvantage. She minimized atmospheric fluctuations by restricting exposure time in imaging the stars. Meticulously, she charted their movements. Success or failure depended on choosing the right stars to follow. At first, both teams were following a star designated SO1. But Gez's attention was drawn to another star.
Another star, which people were very excited about in the earliest days, was SO1. It was the star that was moving fastest initially. But it was SO2 that, as it got closer to the black hole, has become the fastest moving star that we've known about.
This graphic represents Gez's findings. Knowing that stars orbit the center of the galaxy was not enough to prove the existence of a black hole. In January of 2002, another star, designated SO2, was observed to be behaving strangely. It was executing a blindingly fast and tight orbit, clocked at 5,000 kilometers per second, as if being swung violently around and around.
These were incredibly exciting times because, of course, at every stage of this experiment, people said, you can't do it, or what you're seeing isn't what you should be seeing. So we initially saw that they were moving fast, and people said, well, these stars aren't bound to the galaxy. You're not going to see them curve.
Yet SO2 was indeed curving in a rapid orbit. This is an actual imaging sequence. Exhaustive analysis showed it to be a giant star with a mass equivalent to 10 suns.
The only thing that can make stars move that fast is a lot of mass. These stars are moving because there's a lot of gravity. And the only thing that makes that much gravity in that small a space is a supermassive black hole.
With their adaptive optics, the strange behavior of SO2 had not escaped the notice of the European team either. They succeeded in imaging SO2 at around the same time.
Of course, that was the moment everybody was extremely excited about, that we saw, wow, that orbit is proving there must be a mass, and we can measure the mass, we can actually calculate the mass. It's an easy calculation, any student can do it, and the result is extremely fascinating. This mass, which we are seeing in these images, is 4 million times the mass of the Sun.
Finally, after 10 years of observations, it was determined that a supermassive black hole does in fact exist in the center of our galaxy. And it is bigger than was imagined, by many orders of magnitude. Black holes created when stars die are typically 50 kilometers in diameter at most, but the one at the center of our galaxy is gigantic. The diameter is estimated to be 24 million kilometers. That's like 17 of our suns lined up in a row. Round this monster black hole rushes SO2, a giant blue star, at 5,000 kilometers per second, about 200 times the speed at which the Earth orbits the Sun. That is a speed made possible only by the immense gravitational pull of a black hole. In the center of our own galaxy, but far from Earth, unfolds a dance of the stars. It was this dancing of the stars that proved the existence of a supermassive black hole.
It was an idea, but, you know, far out and not very much considered as natural, and it remained that way for about 15 years.
Lyndon Bell had predicted that a supermassive black hole exists at the center of every galaxy. Apart from observing the orbits of the stars, there's another way to prove the existence of such a black hole. That's to observe the moment when a black hole swallows up stars or gases. As gases are sucked into a black hole, they first flatten into a disk. Friction causes them to superheat and to emit intense radio waves. If these radio waves can be detected, that can indicate the presence of a black hole. The largest telescope in the world for detecting extremely high-frequency millimeter band radio waves is the 45-meter radio telescope at the National Astronomical Observatory of Japan. It was in fact a Japanese scientist who first proved Lyndon Bell's theory that a supermassive black hole lies hidden in every galaxy. It happened in 1990, 21 years after Lyndon Bell's prediction. Naomasa Nakai was working at the Nobeyama Radio Observatory, studying gases at the centers of galaxies. He was interested in a galaxy adjacent to the Big Dipper. Galaxy M106, a spiral galaxy 21 million light-years from Earth. Radio waves had been reported to be issuing regularly from the nucleus of M106.
銀河の中でそういう規則正しく電波、光もそうですけど、変わるというのは、そういう現象はほとんどないんです。だから非常に驚いてですね、本当にそういう、電波の強さが規則正しく変わっているのかどうかというのを調べようとしたんです。
In addition to a 45-meter diameter parabolic dish antenna, the Nobeyama Radio Observatory has some world-class instrumentation. 8 spectrometers capable of minute observation of radio waves. A single spectrometer is sufficient to observe radio waves from the nucleus of a galaxy. But to be thorough, Nakai used 2 spectrometers for the very center of the galaxy and flanked them with the 6 remaining ones. That decision to use all 8 instruments led to the discovery of the century. Nakai had simply wanted to put all his spectrometers to some use, but the results astonished him. There were surprising spikes on both ends of the combined graphs. Nakai was especially struck by the ones on the left. This indicated something moving at high velocities never before observed.
今まで銀河でですね、そういう大きな速度を見つかったことは全くないわけです。これに気がついた時にはもう体中がですね、熱くなりましてですね、これはとんでもないことだというふうに思いましたけど。
More detailed observations were made using a high-resolution telescope. They found something remarkable at the core of the galaxy. A spinning disk. This was a structure very like the disk formed by gases being sucked into a black hole. The spikes recorded by the 8 Nobeyama spectrometers were from this disk. The disk was spinning furiously, 3.6 million kilometers an hour. Detailed analysis revealed that the mass at its center was equivalent to 39 million of our suns. It was indeed a monster black hole.
45メーターなければそういうブラックホールは見つかってなかったです。それから電波分光計が8台なければですね、とても見つかってなかったですね。
When his discovery was published in 1995, Nakai received a letter. The letter read, "I have been waiting 26 years for such proof, and congratulate you on your great discovery." The letter came from England. The sender? None other than Donald Lyndon Bell, who had predicted the existence of supermassive black holes.
I was very happy because I didn't feel that I absolutely knew. I thought it was likely, and I thought it was more and more likely.
A black hole equivalent to 39 million solar masses was sucking in huge volumes of gas with its tremendous gravitational force. The dark object in the center of this artist's conception is a black hole. Its diameter is awesome, as if 160 of our suns were lined up in a row. It is now thought that almost all galaxies have these supermassive black holes at their center. The most advanced observational instruments are detecting ever larger black holes. Situated outside Earth's atmosphere, the Hubble Space Telescope can see space objects with great clarity. Hubble took aim at NGC 7052, a galaxy located 37 million light-years away. The image it captured was that of a huge disk, comprised of gases and stars. In its center, there ought to be a supermassive black hole.
When we got this image, I was just super excited. I mean, because it was such beautiful, rich detail that I really knew right when I saw this that we were going to be able to get, excellent spectra and really be able to determine whether this galaxy has a black hole and how massive it is. So I was very, very excited.
The galaxy was indeed harboring a supermassive black hole. A black hole equivalent to 300 million solar masses. That's more than 70 times larger than the one at the center of our own Milky Way galaxy. A black hole with a diameter of 1,200 of our suns lined up in a row. And Hubble has spotted an even larger one, an ultramassive black hole. This one is in M87. 59 million light-years away. Scientists had long been puzzled by a band of white light there. When Hubble was trained on the galaxy's core, the band of white light was revealed to be a gigantic jet of gases. As the gases are sucked violently into the black hole, a portion of them are ejected in the form of this jet. The mass of the black hole at the base of this jet has been calculated to be 6.4 billion solar masses. That's 10 million times greater than the supermassive black hole at the center of our Milky Way galaxy. In size, its diameter is equal to 25,000 of our suns lined up in a row. Then, in 2011, the largest black hole in history was discovered. In the galactic nucleus of NGC 4889, there's an unimaginably monstrous black hole, with a mass equivalent to 9.7 billion times that of our sun. What scientists are most eager to elucidate now is the process by which these black holes become so large. They may start with the death of a star, but how do they then grow to billions of times their original size? Trinity College at the University of Cambridge. Isaac Newton, who formulated the universal law of gravitation, conducted research here. Martin Rees has served as Master of Trinity College. Rees has conducted research on supermassive black holes together with Lyndon Bell. The impetus for his research was the discovery of galaxies whose high-energy cores were emitting powerful radio waves.
Well, there were various alternative theories about what might be happening in the centers of the galaxies, which are putting out a concentrated high source of power. And these ideas included a very dense cluster of stars, a very massive star, a binary supermassive object, etc. And I realized that if you followed forward the likely evolution of any of these objects. They would all have no alternative to becoming a big black hole.
So any object emitting sufficiently high amounts of energy will inevitably become a supermassive black hole. How then are supermassive black holes born? The Rees diagram, as it was called, charted the possible routes.
If you're going to be at that, you need to have...
In the 30 years since the Rees diagram was published, there has been a succession of discoveries of supermassive black holes. At the same time, the study of their birth has also been progressing. One scenario suggested by Rees was the consolidation of several smaller black holes. At the end of their lives, stars explode, forming relatively small black holes. Hundreds of millions of them may cluster together, merging into one supermassive black hole. This is NASA's space-based Chandra X-ray Observatory. Chandra has been examining a region where black hole consolidation is thought to be taking place. Galaxy NGC 6240 is located 400 million light-years from Earth. Actually, two galaxies are colliding there. As Chandra examines their galactic cores, two bluish-white spots appear. They are both massive black holes, one at the center of each galaxy.
This blue region here is a blow-up of the center, and you can see there are two little sources there, one brighter and one a bit fainter. But each of those, when we look at the spectrum, shows a very characteristic sign that this is just emission from a supermassive black hole in each case, which has never been seen before until we had the beautiful Chandra image and could separate the two.
Two black holes in close proximity to each other, but they cannot soon merge. Rather like the Earth and the Moon in their perpetual dance, the two black holes orbit about each other without colliding. So what about Rees's concept of black holes merging to form a supermassive black hole? Masayuki Umemura uses a supercomputer to create simulations of black hole mergers. Here, he simulates the behaviors of 10 black holes of equivalent mass. The first consolidation happens far sooner than expected. It takes only 50 million years. The process repeats. Within about 500 million years, 5 black holes have merged into one.
もともと銀河が持っていたブラックホールが、大きな銀河に取り込まれたときにブラックホールごと、中に取り込まれるわけですね。そうすると2つではなくて、例えば大きな銀河の中に10個のブラックホールがあるというような状況が最初に起こった可能性が高いということをまず想定しました。
Let's look at our actual universe. There are galactic collisions and mergers all over the place. And when galaxies merge, the thinking is that their black holes merge too. Wherever galaxies cluster, there's bound to be a cluster of black holes. That means a process of consolidation of black holes. This conforms to actual observations of our universe. A second Rees diagram scenario has a seed black hole becoming supermassive by swallowing up gases and stars. In that scenario, the monster is born by gulping down an unbelievable quantity of gases, equivalent to hundreds of millions of our sun. The gases are sucked in with so much force that the friction produces incredible heat. That violent process emits intense light and X-radiation and blows away surrounding gases. The result is that there are no more gases to feed on, and the black hole ceases to grow. But how is it that such a huge quantity of gases could be sucked in the first place? Gases that are being sucked in, blowing away other gases. Ken Osuga studies this contradiction. He has found a particular mechanism within black holes by which they can continue to draw in vast amounts of gases. He's prepared a simulation of one scenario for how supermassive black holes may be created. As a black hole sucks in gases, it generates magnetic field lines, which penetrate the surrounding gas disk like hoops. Thus embedded, they are then distorted by the swirl of the disk. As the disk swirls, the magnetic field lines are caught in a spiral vortex, twisted and coiled like a spring. This is a plasma jet. A portion of the disk's gases, charged with energy such as light, shoots out in opposite directions perpendicular to the disk. Any remaining gases are sucked into the black hole, which grows supermassive.
私たちの研究の結果はですね、光の力が非常に強くなったとしても、ジェットは噴出するけども、ガス円盤からガスは変わらず吸い込まれ続けるということを明らかにしました。これによってですね、ブラックホールは大量のガスを吸い込むことができますので、巨大ブラックホールに成長するのに一役買うということを証明することができました。
Hubble has captured this actual image of an intense jet erupting from the center of a galaxy. The gas-guzzling scenario for supermassive black hole creation, as outlined in the Rees diagram, thus seems persuasive. Martin Rees developed several theories of supermassive black hole formation. One was by the continuing consumption of gases. Another was by the consolidation of smaller black holes. But the Rees diagram indicated a third possibility as well. Under this third scenario, just after the creation of the universe, large clouds of gas condensed into supermassive black holes directly, without first becoming stars at all. Recently, evidence for this third scenario has also come to light. By combining information from the Chandra X-ray and Hubble Space Telescopes, Priya Natarajan hunts for supermassive black holes created at the inception of the universe. These far-off galaxies were photographed by Hubble. Among those circled on the screen are some that are 12 billion light-years away. They are small galaxies, born immediately after the universe itself. Some 200 of them have been identified. Here's one as perceived by Chandra. And it already has a supermassive black hole in it. Natarajan was surprised to discover that almost all 200 of them had supermassive black holes in them. If so many supermassive black holes were already present immediately after the creation of the universe, then that lends powerful support to the third scenario in the Reese diagram.
So just as we think that a gas cloud that is collapsing could make the first star reasonably easily, the conditions that you need for making a black hole seed directly without forming a star, instead of forming a star, also exist in the early universe.
Efforts are also underway to confirm the third Reese diagram scenario computationally.
I think it is the first time that there is a model showing that it is possible to produce a precursor of a big black hole in the form of this supermassive black hole.
This is a giant gas cloud, 100 light years in diameter. 70,000 years after it formed into a gas cloud, its gases were compressed into a disk 1 light year across. The gas disk was equivalent in mass to 100,000 of our suns. It then condensed further, compressed by its own weight, giving rise to a supermassive black hole. So the third scenario in the Reese diagram, going directly from gas cloud to black hole, is a real possibility. Studies of the origins of these supermassive black holes are ongoing. The latest research reveals that the supermassive black holes do not simply grow fat, consuming everything nearby. Surprisingly, they exert a huge constructive effect on the space around them. What these remarkable monsters call home is a galaxy's core. More specifically, it's inside the concentration of stars called the bulge. The shape and size of the bulge varies with each galaxy. John Cormandy has investigated the relationship between the mass of a bulge and of its supermassive black hole. The first galaxy he observed was Andromeda. The supermassive black hole here is equivalent to 150 million solar masses. The bulge is approximately 1,000 times greater in mass. Next, he looked at the Sombrero galaxy. The black hole here is 1 billion solar masses. The mass of the bulge is approximately 1,000 times that. Plotted on a graph coordinating the masses of the bulges with those of the black holes, the galaxies form a nearly straight line. In most galaxies, the black hole to bulge ratio of masses is 1 to 1,000. This strong relationship between the mass of supermassive black holes and their galaxies' bulges surprised many scientists.
We know that when gas densities get very big, you get a burst of new stars being formed. And so at the same time when this burst of stars is making the bulge, the rest of the gas is being fed to the black hole and making the black hole bigger. So you get lots of new stars, and you get higher mass black hole, and the two correlate.
A galaxy comprises hundreds of billions of stars. It turns out that at the galactic cores, the black holes and the bulges have a deep interrelationship. A giant bulge will correlate with a giant black hole, a small bulge with a small black hole. This strange law of outer space may mean that galaxies and black holes evolved together. Andrea Ghez discovered the supermassive black hole at the center of our own Milky Way galaxy. She also found evidence that it performs an astonishing function within the galaxy's bulge.
We've had one surprise after another in our study of the center of the galaxy. What we see is that they're very massive stars, which tells us that they're very young stars. And the last thing you expect near a black hole is to find a very young star, because black holes are very inhospitable to star formation. They should just tear apart any cloud that might eventually become a star. So you really don't expect to see young stars, baby stars near a black hole. And yet all the stars that told us that there's a black hole are the ones we predicted shouldn't be there. So it's one mystery after another.
Near the supermassive black hole at the center of the Milky Way, Ghez found many baby stars. This suggests something astounding, that new stars may be emerging from the gases that originally accumulate around a black hole. The effect black holes have on surrounding space is not limited to the birthing of stars. A project spearheaded by NASA called Tanami is endeavoring to capture distant galaxies. Tanami involves the participation of radio telescopes in a dozen locations in the southern hemisphere, chiefly in Australia, but also in Chile, South Africa, and the South Pole. One of its targets is a galaxy located 14 million light-years from Earth, Centaurus A. This is the image they obtained, a clear view of a plasma jet violently shooting out from an invisible black hole. The jet bursts out at 30% of the speed of light. Analysis of this jet turned up something quite unexpected. The jet shooting out of the black hole even escapes the galaxy itself. Its plume expands for a distance of 1 million light-years. So the black hole doesn't just guzzle down gases, it sends out the stuff that stars are made of far beyond its own galaxy. The role of the supermassive black holes in the universe is still largely mysterious, but scientists are learning more and more.
Cosmos looks the same from Britain and from Japan. Indeed, the night sky is the same to all of us and has been the same to all our ancestors throughout human history. It's the one common feature of all humanity. They've all looked up at the night sky and wondered at it and interpreted it in their own way. It's a wonderful story where we found all these extraordinary objects in the universe, and we can understand these vast cosmic horizons in a way that our ancestors could only have dreamed of. So it's a wonderful story.
Supermassive black holes, monsters in the galactic cores. They may gobble up everything around them, but they also give birth to stars and send out energy-rich materials into the universe. Some came into being at the same time as their galaxies and grew along with them. He was interested in a galaxy adjacent to the Big Dipper. Galaxy M106, a spiral galaxy 21 million light-years from Earth. Radio waves had been reported to be issuing regularly from the nucleus of M106.
銀河の中でそういう規則正しく電波、光もそうですけど、変わるというのはそういう現象はほとんどないんです。だから非常に驚いてですね、本当にそういう、電波の強さが規則正しく変わっているのかどうかというのを調べようとしたんです。
In addition to a 45-meter diameter parabolic dish antenna, the Nobeyama Radio Observatory has some world-class instrumentation. 8 spectrometers capable of minute observation of radio waves. A single spectrometer is sufficient to observe radio waves from the nucleus of a galaxy. But to be thorough, Nakai used 2 spectrometers for the very center of the galaxy and flanked them with the 6 remaining ones. That decision to use all 8 instruments led to the discovery of the century. Nakai had simply wanted to put all his spectrometers to some use, but the results astonished him. There were surprising spikes on both ends of the combined graphs. Nakai was especially struck by the ones on the left. This indicated something moving at high velocities never before observed.
今まで銀河でですね、そういう大きな速度に見つかったことは全くないわけです。これに気がついた時にはもう体中がですね、熱くなりましてですね、これはとんでもないことだというふうに思いましたけど。
More detailed observations were made using a high-resolution telescope. They found something remarkable at the core of the galaxy. A spinning disk. This was a structure very like the disk formed by gases being sucked into a black hole. The spikes recorded by the 8 Nobeyama spectrometers were from this disk. The disk was spinning furiously, 3.6 million kilometers an hour. Detailed analysis revealed that the mass at its center was equivalent to 39 million of our suns. It was indeed a monster black hole.
45メーターなければそういうブラックホールは見つかってなかったです。それから電波分光計が8台なければですね、とても見つかってなかったですね。
When his discovery was published in 1995, Nakai received a letter. The letter read, "I have been waiting 26 years for such proof, and
4 million times the mass of the sun.
Finally, after 10 years of observations, it was determined that a supermassive black hole does in fact exist in the center of our galaxy. And it is bigger than was imagined, by many orders of magnitude. Black holes created when stars die are typically 50 kilometers in diameter at most, but the one at the center of our galaxy is gigantic. The diameter is estimated to be 24 million kilometers. That's like 17 of our suns lined up in a row. Round this monster black hole rushes SO2, a giant blue star, at 5,000 kilometers per second, about 200 times the speed at which the Earth orbits the Sun. That is a speed made possible only by the immense gravitational pull of a black hole. In the center of our own galaxy, but far from Earth, unfolds a dance of the stars. It was this dancing of the stars that proved the existence of a supermassive black hole.
It was an idea, but, you know, far out and not very much considered this natural, and it remained that way for about 15 years.
Lyndon Bell had predicted that a supermassive black hole exists at the center of every galaxy. Apart from observing the orbits of the stars, there's another way to prove the existence of such a black hole. That's to observe the moment when a black hole swallows up stars or gases. As gases are sucked into a black hole, they first flatten into a disk. Friction causes them to superheat and to emit intense radio waves. If these radio waves can be detected, that can indicate the presence of a black hole. The largest telescope in the world for detecting extremely high-frequency millimeter-band radio waves is the 45-meter radio telescope at the National Astronomical Observatory of Japan. It was in fact a Japanese scientist who first proved Lyndon Bell's theory that a supermassive black hole lies hidden in every galaxy. It happened in 1990, 21 years after Lyndon Bell's prediction. Naomasa Nakai was working at the Nobeyama Radio Observatory, studying gases at the centers of galaxies. Shine much more clearly. Gez, who did not yet have adaptive optics, was at a disadvantage. She minimized atmospheric fluctuations by restricting exposure time in imaging the stars. Meticulously, she charted their movements. Success or failure depended on choosing the right stars to follow. At first, both teams were following a star designated SO1. But Gez's attention was drawn to another star.
Another star which people were very excited about in the earliest days was SO1. It was the star that was moving fastest initially. But it was SO2 that, as it got closer to the black hole, has become the fastest moving star that we've known about.
This graphic represents Gez's findings. Knowing that stars orbit the center of the galaxy was not enough to prove the existence of a black hole. In January of 2002, another star, designated SO2, was observed to be behaving strangely. It was executing a blindingly fast and tight orbit, clocked at 5,000 kilometers per second, as if being swung violently around and around.
These were incredibly exciting times because, of course, at every stage of this experiment, people said, you can't do it, or what you're seeing isn't what you should be seeing. So we initially saw that they were moving fast, and people said, well, these stars aren't bound to the galaxy. You're not going to see them curve.
Yet SO2 was indeed curving in a rapid orbit. This is an actual imaging sequence. Exhaustive analysis showed it to be a giant star with a mass equivalent to 10 suns.
The only thing that can make stars move that fast is a lot of mass. These stars are moving because there's a lot of gravity. And the only thing that makes that much gravity in that small a space is a supermassive black hole.
With their adaptive optics, the strange behavior of SO2 had not escaped the notice of the European team either. They succeeded in imaging SO2 at around the same time.
Of course, that was the moment everybody was extremely excited about, that we saw, wow, that orbit is proving there must be a mass, and we can measure the mass, we can actually calculate the mass. It's an easy calculation, any student can do it, and the result is extremely fascinating. This mass, which we are seeing in these images, is...
The way you do this is by pointing your telescope at the center of the galaxy and using a technique that allows you to see the stars around the black hole. So here's the black hole. And what you want to do is we want to be able to see a star. You want to be able to see a star make a complete orbit around the center.
Guess followed the movements of the stars for years, plotting their trajectories. If they were in fact orbiting some unseen object, then that would be proof of a black hole. The center of the Milky Way, however, is 26,000 light years from Earth. Ascertaining the movements of stars around a point so far off in space is no easy matter. Mauna Kea, Hawaii, home to several giant telescopes. Gez used one of the observatories on this summit, the Keck Observatory. The Keck has two of the largest telescopes in the world, with primary mirrors that are 10 meters in diameter. Gez's observations here began in 1995. But Gez and her team were not the only ones searching for a supermassive black hole in the center of our galaxy. A European team based in the heart of Germany had also been hunting the same monster. The leader of these star trackers is Stefan Gillesen.
They have a 10-meter telescope. We have an 8-meter telescope. So our telescope is a bit smaller. However, we are on the southern hemisphere, where the galactic center is visible for more hours. So we can observe from February to October.
The European team conducts its observations at the Paranal Observatory in Chile. The VLT array there comprises 4 8.2-meter telescopes. But even with such advanced technology, success is elusive. The problem is Earth's atmosphere. Atmospheric fluctuations blur the stars. April 2002, the European team installs epic-making new equipment. From the VLT at Paranal, they shoot laser beams into the night sky to measure and adjust for those atmospheric fluctuations. Their special equipment succeeds in doing just that. The new method is called adaptive optics. It brings the stars into focus. Corrected for atmospheric fluctuations, the stars shine. The black hole is a bizarre space object, defined by the absence of everything except gravitational force. How do scientists wrap their minds around it? It's complicated. Seriously massive objects warp the fabric of space. The heavier the star, that is, the greater its mass, the greater the distortion. So light, which would otherwise travel in a straight path, gets bent. If a star of any given mass shrinks sufficiently, its density increases until its local distortion of space is infinite. That's a black hole. A border develops separating the black hole from the space around it. Once this border has been crossed, going into the black hole, even light cannot escape. Border diameter is determined by the weight of the compressed mass. A hole with the same mass as Earth would be merely 2 centimeters across, something the mass of the Sun, 6 kilometers. That's considered the size of the black hole. Black holes are created the instant stars die. Let's say a star 20 or more times larger than our Sun reaches the end of its life and explodes. The star's own gravity then causes its remaining core to implode infinitely, becoming a purely gravitational force. When a black hole is born,
ripped to shreds in a flash, collapse in on itself, or will it slowly freeze to death? Scientists are imagining the unimaginable, and they're coming up with some wild ideas about how it's all going to end. This is the end of the universe. A battle is taking place in the farthest reaches of space. No one can see it, but scientists are certain that it's happening, and that the outcome is grim. The universe is going to end. It won't happen for billions of years, but there is no way out. Figuring out how it will end is the challenge of astrophysicists around the world. They're pointing high-tech equipment out toward the heavens to unlock the secret of our fate. The possibilities are frightening. In one scenario, gravity pulls the universe back into itself, similar to air being let out of an inflated balloon. The universe goes back to its original size. This is the Big Crunch.
That'd be the end of the universe, and a big fireball, as all the matter collapses onto itself. That'd be pretty dramatic.
Then there's the Big Chill. The universe expands until the nuclear furnaces that power all the stars burn out. The universe grows cold and dies.
A second possibility is actually kind of sad. The universe will continue to expand forever, and it will just grow into an increasingly cold and lonely place as the expansion removes our nearest neighbors from us, and we just end up a single isolated community of stars and galaxies.
Then again, there could be a much more spectacular end in which everything is ripped to shreds, down to the last atom. Think of it like a balloon that is filled with too much air. It pops.
It's much more dramatic than the Big Chill, and just as fateful as the Big Crunch. The universe continues to expand, but at an ever-quickening pace. And in fact, the pace is so great that even the space-time fabric cannot hold the universe together.
However the end comes, it will be a dramatic conclusion. To understand how it all could end, scientists turn to how it began. The mystery starts to be solved here, at the Mount Wilson Observatory overlooking Pasadena, California. In 1929, while looking through what was then the world's largest telescope, Edwin Hubble makes a strange discovery. The universe is expanding.
Hubble's discovery led to a whole new picture of the universe, that it was a dynamic environment and that it evolved. It changed in time, and that's different from pictures that people had of cosmology previous to that.
Before Hubble, scientists said that the universe was static and unchanging. Hubble's discovery that the universe is expanding meant it had a starting point, a beginning.
That brought the idea forward that, hey, what if we ran the film backwards in time and found the point at which that began?
The Big Bang. That fraction of a second when the universe and everything in it exploded into existence from a point smaller than an atom.
One common misconception about the Big Bang is that we can identify a point in space where the Big Bang occurred. But in fact, it's more appropriate to think of the Big Bang as a simultaneous creation everywhere of space, which is then continuing to expand to the present day.
Scientists theorize that at the moment of the Big Bang, the first small particles of matter called quarks were produced. They collided to form the building blocks of the universe. These floated in a thick fog of hot plasma for about 400,000 years. Gravity, also created at the Big Bang, drew the particles together, eventually creating the first stars and lighting up the cosmos.
The theory of the Big Bang is a very solid theory. What happened at the moment of the Big Bang is still something we're working on. We don't really understand.
If the universe has been expanding since the Big Bang, scientists must consider that it will stop expanding at some point. The question is, how? The most obvious answer involves gravity. What goes up must come down. Stars and galaxies and everything else might reverse direction. The universe would collapse in what some scientists call a big crunch.
Take the top and then see the other handle and just jerk them apart.
A model rocket offers clues to how the big crunch would work. The rocket is like the universe expanding into space out of the Big Bang. An initial bang allows the rocket to overcome the pull of gravity.
5, 4, 3, 2, 1.
Eventually, when the fuel is exhausted, the rocket coasts a few feet higher, stops, and is pulled back to Earth. This is what would happen with a big crunch. The entire universe is essentially pulled back to its launch pad.
The universe itself has its own momentum, its own energy. It's moving outward. But eventually, there's a point where possibly the universe will stop that moving outward, just like the rocket that we saw, and have to fall back in upon itself and collapse again under the force of its own gravity.
In this scenario, the universe could return to its original state just before the Big Bang, setting the stage for a perpetual seesaw of creation and destruction. The Big Crunch theory moved to a scientific back burner. Cosmologists figured out that there must be some form of energy that keeps the universe from collapsing. The existence of such a force leads to new theories about what the universe is made of and how it might end. And evidence about how this might play out is found in some of the most powerful and mysterious phenomena in the cosmos: black holes. Predicting how the universe will end involves some of the most advanced technology known to man. On a remote volcano on the island of Hawaii, astronomers are monitoring a battle in space that is shaping the fate of the universe. At an elevation of nearly 14,000 feet, the Keck telescopes bring astronomers from all over the world nearer to space for a clearer view of the cosmos. They come here because the telescopes work best far away from city lights and as high as possible above Earth's polluted air. Harsh conditions make it difficult to work here, but for scientists in pursuit of the great mysteries above, it's paradise.
So this is a remarkable location, but of course the air is very thin, it's extremely hard to work here, but these telescopes are amazingly powerful. But we're ambitious astronomers. We don't just stop looking at easy objects. We try hard to look at the very faintest objects so we can understand the extremities of the universe.
Here, astronomers like Richard Ellis are working on a problem that has been all-consuming for cosmologists since Edwin Hubble. They know the universe is expanding, but what they don't know is how fast. It will be difficult to predict exactly how the universe will end until they solve this mystery. The answers lie in the past.
Now, what I did the focus on was a V equals 12.
There it is. Okay, that's the dry star.
Get a better focus now. That was worth doing.
An astronomer like myself uses a ground-based telescope as a time machine. We're looking back in time to study distant galaxies, seen as they were a long, long time ago.
One of the distant galaxies that astronomers found revealed a powerful source of X-rays from something that they could not see. It was in the constellation Cygnus and emitted no light, but something was there. Whatever was emitting these X-rays had a mass about 7 times that of Earth's sun. There wasn't a name for it, so they called it a black hole. Black holes offer scientists an analogy to how the Big Crunch theory works. When certain stars run out of fuel, they collapse in on themselves into a smaller and far denser mass that attracts more and more matter, just like the Big Crunch. The gravitational pull is so powerful that anything that falls near a black hole will be forever trapped. Not even light can escape. It's a mind-boggling concept that something invisible is detectable and offers a view to our ultimate fate.
This black tarp represents space, and space is relatively flat, but when you put a massive object into space, it curves it. This is a penny, and notice how it comes into a really beautiful circular orbit. Basically, the black hole trapped it into an orbit around itself. And that orbit becomes very circular as it gets closer. And now the penny will eventually disappear, go inside the black hole.
Earth's sun warps space similarly to a black hole, only it's a cosmic wimp by comparison. The gravitational pull of our sun is much weaker. Earth and all its nearby planets are trapped by the sun's pull, but it's so mild that it just stays in orbit without being sucked into the sun. The mass of a black hole can be 1,000,000 times the mass of the sun, or more, causing a huge warp in the space around it that consumes everything that comes near.
That black hole wraps space around itself. And so if material falls near it, it falls inside and gets trapped forever.
Black holes exist in isolated areas throughout the cosmos. A black hole's gravitational pull is a scaled-down version of the force that could cause the universe to collapse. That force is dark matter, and dark matter is what scientists often call cosmic glue.
Hi, Matthew. So let's do some cosmology here. Dark matter attracts other objects via its gravitational attraction. It's a positive force.
There's another force that opposes gravity, and that is dark energy.
Dark energy, we don't really understand what it is, but it's a negative repulsing effect that pushes galaxies away from each other.
The whirlpool in Richard Ellis's demonstration represents the gravitational force of dark matter. The green dye coming out of the syringe shows how the stuff of the universe collapses under the force of dark matter.
The presence of dark matter acts as the focus for the gas in the universe, bringing structure together. This is how the Milky Way developed as the universe expanded. Little things merging into big things, the positive, constructive force of gravity. Now, if this was the only force in the universe would stop expanding at some point in the future, and eventually the universe would start collapsing. Gravity would eventually halt the expansion, bring it back together in a big crunch.
Yet the universe continues to expand and isn't showing any signs of collapsing. This suggests the opposing force of dark energy could be stronger than dark matter. But it will take scientific detective work to find out. They look to one of the most violent forces in the universe for clues.
We're studying exploding stars to try to understand if they can tell us the rate at which the universe is expanding.
These are explosions at the end of the lives of stars, not unlike our sun. The fuel that these stars have in their centers is spent. The star collapses, the outer part expands, and the star becomes something called a white dwarf.
White dwarf stars sometimes have other stars orbiting nearby, a companion star. A massive explosion could happen if the companion star's debris falls onto the white dwarf, causing a spectacular fireworks display in the cosmos. Scientists consider exploding stars, or supernovae, like in these images captured by the Hubble telescope, to be reliable telltales of how fast the universe expands. Their brief and bright explosions allow scientists to track the universe's expansion and give them a way to measure its speed.
Essentially, they are white dwarf stars that become nuclear bombs. They explode with a certain brightness and a certain length of time. It takes a certain amount of time for that brightness to dissipate. They are essentially standard candles. Any one of these will look the same no matter where it is in the universe.
Astronomers measure the distance and speed of these exploding stars by measuring the amount of red light they emit. The faster the star moves away from us, the redder its light appears. The expansion rate of galaxies containing stars like supernovae can then be used to interpret how the rest of the universe is moving outward.
We know this because we can compare the velocities of galaxies with their distances.
These are the clues that lead astronomers to answer just how soon the universe will reverse direction and come back together in a big crunch. Or, this information might lead to an entirely different conclusion. Dr. Ellis is looking at clues at the Keck Observatory in Hawaii. While the telescope is on the top of a huge volcano, He's in a viewing room on another part of the island.
Hey, emission lines, Johan.
Oh, you see it?
In the red side, I think.
At the same time, Johan Richard is at the California Institute of Technology in Pasadena, California, evaluating the light from a distant galaxy that the Keck telescope captured in Hawaii. He's looking to see if any of the known elements coming from the galaxy are in the red spectrum and moving farther away.
We can interpret that as a velocity, as how much the galaxy is moving away from us. We can really interpret how the entire universe is behaving, is expanding.
Interpreting redshift is the cornerstone of the quest to pin down the fate of the universe. Clearer pictures of the universe that have only been possible in recent years have led cosmologists to conclude that the redshift of distant galaxies is greater than predicted. This is startling. Not only is the universe expanding, it's speeding up. Nothing in the observable cosmos could account for an accelerating universe, and yet the data seem irrefutable. This has to mean that an invisible force is working against gravity. Cosmologists have come up with a name: dark energy.
So when the universe was young, gravity was the most dominant force. And so what we see here is galaxies as particles on the surface of the water are bound together by gravity. And at a point about 7 billion years ago, dark energy and gravity are pretty well in balance. But the universe continues to expand, the density goes down, and so dark energy starts to take over. And lo and behold, the universe starts to accelerate. So dark energy is now the dominant property of space.
So the universe started out with a certain amount of energy, and we know we're trying to understand how much energy there is, and we know the universe is expanding as it moves outward with time. We also know now that the universe's expansion is accelerating, and we don't know, is that acceleration going to slow down or not? We're still trying to understand that. So in understanding what's going to happen to the fate of the universe, we have to know how much energy is there, how much matter is there.
The history of the universe is really a battle between dark matter and dark energy. These two forces are in opposition, and so both the history of the universe and its ultimate fate is really the competition between these two forces.
The Big Crunch theory was a result of scientists interpreting that dark matter is the dominant force. But astronomers now suspect that dark energy might be much stronger. If so, the end could be dramatic and violent.
It pulls apart solar systems, it pulls apart stars, and eventually it grows so strong that it pulls apart matter itself, breaks bonds, pulls apart atoms, and reduces everything to fundamental particles, and that's the end of the universe.
The battle between dark matter, the force that holds the universe together, and dark energy, the force seeking to tear it apart, has set the universe on a path of destruction. If dark matter is the victor, the universe might collapse. If dark energy rules the cosmos, it could rip to shreds.
The expansion grows so strong that it tears up the entire universe.
It'll be a strange twist of fate. Dark energy, the force that propelled matter to form a magnificent universe, continues to push it outward and drives it to its demise. To find out if dark energy is in fact winning the battle, scientists will first need to know how fast the universe is actually expanding.
The most remarkable feature of the universe is that it's expanding. Every galaxy is moving away from every other galaxy. When you look out into the night sky, you see distant stars, galaxies, clusters of galaxies they observe with telescopes, and they're all moving away from us. We can illustrate that with this balloon. As we expand it, we see that every dot drawn on this black balloon, like the night sky, is moving away from every other dot. But there's something else that we know about the universe, something else that we know about the expansion. That is that the expansion is getting faster. The universe is accelerating. The size of the universe is getting bigger at a faster and faster rate. And we don't know exactly how fast it's accelerating, but if it's accelerating fast enough, then something really dramatic could happen. The universe could end up tearing itself apart in a big rip.
This is perfect. This is great that you rigged this up. So this is a giant version of the demo that I do in class.
Dr. Robert Caldwell attempts an earthbound experiment to show how dark energy affects the acceleration of the universe. He uses a paintball gun mounted on a truck.
Yeah, and basically, I mean, we could adjust the angle in any way that you want it. What do you think about this?
Yeah, I think down at the
down
ground,
a little bit
you know,
more
is the best, so we can mark each
How's
time
that?
the gun fires. That'll be good.
All right, let's try that.
He sends the truck coasting down an incline. Earth's gravity pulls the vehicle downhill, which is similar to how dark energy propels the universe outward, causing it to expand. Gravity pulls the truck forward at an increasing speed. The gun fires paint at the ground at regular 1-second intervals. Caldwell measures the distance between the paint dots to calculate just how fast the truck was accelerating. He'll use the data from this experiment to see how gravity's force compares to dark energy's force in the cosmos.
We started thinking about the Big Rip when it was discovered that the expansion of the universe was accelerating. The degree of acceleration is not known, and it's the subject of a lot of effort by astronomers today to try and figure out exactly how fast the expansion is growing. What is the past evolution of the universe in detail, and if we can glean from that, what is the future evolution of the universe? It's not known exactly how fast it's accelerating. There's some evidence that the acceleration is beyond a certain threshold, and beyond that threshold, there's a runaway effect that could take place, and it would rip apart the universe.
Good luck.
Fantastic. I think we've got some good data.
Excellent. How do we measure this?
Great. Give you that end.
All right.
I'll take this.
5 feet 8.5 inches.
The point of the paintball experiment is to find parallels between the truck propelled by the invisible force of gravity and the accelerating universe.
I'm glad we got the long tape measure because it's really growing pretty fast, the interval.
Within a few measurements, the distance between the paint spots increases by nearly 7 times. If the truck were in space, at this rate, it would travel faster than 100 miles per hour within a minute, and over 1,000 miles per hour within 10 minutes.
They're getting big now.
Here we got 42.5 feet.
42, all right, 0.5.
The question for Robert Caldwell is whether the same kind of expansion and acceleration are happening on a cosmic scale.
What's the capsule made of? Is it plastic or something?
Gelatin.
Uh-huh,
It's
okay.
all biodegradable.
Uh-huh.
So you could actually eat them if you wanted to.
This right here is the data that I took with Eric. The cumulative distance traveled by the car as a function of time, and that's beautiful. It's this nice parabolic shape. That's exactly what you expect for an accelerating body. Now over here I've got another calculation going on where I'm working out the acceleration of the universe.
Robert Caldwell's calculation shows that forces on Earth are similar to forces in space. This demonstration, then, gives a sense of the dramatic rate of expansion that appears to be happening in the cosmos.
By eye, it might be difficult to appreciate how good a fit it is, but I can tell you that the weight of the statistics indicates that an accelerating universe is a very good fit to this data.
If, like the truck, the universe is continually accelerating, then billions of years from now, the universe might tear itself apart.
All the distant stars and galaxies will be pulled away from each other. They'll be pulled away from us. But moreover, we won't have time to grow cold and lonely. It'll actually be pretty exciting and dramatic and violent. Stars are ripped apart, planets are ripped apart, and even atoms are torn apart before the universe ends. It wouldn't happen for at least 50 billion years, but still it's an interesting fate for the universe.
What would atoms ripping apart look like? Things like coffee cups are solid. Atoms join together to create something that will hold a cappuccino without leaking a single drop. Zoom in through the cup, like sailing through the cosmos, past the molecules and into the atoms. The solid cup is nothing more than a fabric of atomic particles that formed a bond to become matter. If these particles were to move apart, the bonds that hold this cup together stop working. The atoms no longer support molecules. The connections between the minuscule particles dissolve. Matter in the form of this cup ceases to exist. It disintegrates, gone from existence. This is the dramatic end that Robert Caldwell foresees for the universe.
What you would see if you were standing on Earth or standing on some other planet that happened to still be around at that time, you would see something that looks like a wall of darkness approaching you. And as the wall of darkness approaches, stars would go out, galaxies would go out, and then eventually that wall of darkness would surround the planet. And then pretty soon, atoms themselves are torn apart, and that's it. Just the wall of darkness shrinks down to a point, and that's the end of the universe.
According to Robert Caldwell, that moment is still billions of years off, leaving plenty of time to refine the research.
In a way, this is like a detective story. We're trying to figure out what is the culprit, or who is the culprit responsible for the cosmic acceleration. We think we know its name. We call it dark energy, but we don't know the modus operandi. We don't know exactly how it works. And what's needed is more information about the physics behind the dark energy. We want to know exactly what it does and exactly what it's made out of. And in answering those questions, we'll be able to figure out exactly what is the fate of the universe.
The Big Rip is one theory. Cruising just above Earth's atmosphere and peering deep into space, the Hubble telescope provides scientists with clues to a less violent, but equally unavoidable, end of the universe. Scientists now say the universe is expanding, and that depending on how fast it is accelerating, it might end in a big rip where everything tears apart. It's also possible that it will continue to expand, but at a slower rate. The universe wouldn't rip apart, but would become dark, cold, and lifeless.
If dark energy turns out to be constant, a constant property of space, and continues at the same rate that it is now, the universe will keep expanding forever, and it will be a very sad state. I think in the end, it just chills out. Everything cools down.
Evidence for the Big Chill and all of the theories for the end of the universe, in part, come from the Hubble Space Telescope. It has been orbiting Earth since 1990 and has an unobstructed view of the cosmos. The extraordinary images it beams back to Earth are amazing in their clarity and detail. And because of Hubble, scientists can make better predictions about how the universe will end.
So here is an example of a very deep field that was taken by the Hubble Space Telescope, which literally you point the space telescope at a single region in space. And if you looked at this from a typical ground-based image before Hubble was launched, first of all, it's literally almost size of a postage stamp. And so suddenly, the first Hubble Deep Field that was ever taken had 4,000 galaxies that looked just like the galaxies here, that were never visible before from the ground. A tremendous power. Each of these smudges in their own right is another galaxy. Each one of these galaxies contains about 100 billion stars.
Hubble sees more than just stars and galaxies. it just might be onto one of the key ingredients of space, an invisible ingredient that could put the brakes on dark energy's effect and cause a big chill. That's dark matter. Scientists talk about dark matter as the substance that holds the universe together and could prevent a big rip. Evidence that dark matter exists is seen in some of Hubble's images of nearby galaxies. It sometimes appears as though other galaxies surround them. The other galaxies are not really there at all. Rather, they are reflections of more distant galaxies coming from behind. Astronomers suspect this optical illusion is dark matter causing a weird distortion of light called gravitational lensing. The light from the more distant galaxies is literally bent by the curvature of space caused by stars and dark matter in its path. The more dark matter there is between Earth and the distant galaxy, the more the light will be bent and the greater the force to cause a big chill.
The gravitational lensing is a tremendous tool for the astronomer because we can measure the distortion in background galaxies and use it to trace the distribution of dark matter on various scales. We're looking at a distribution of idealized galaxies here on the sky, and the light from these distant galaxies is passing through clumps of dark matter. What you look at is not really what's happening. It's a bit like wearing spectacles and not knowing that you're wearing them.
And if you can tell how much that bending is occurring, you can map the dark matter, and you can also see, well, if there's dark matter there, is the universe around that dark matter behaving the way it should given the gravity or not? If it's slightly gravitating less, then dark energy might be changing in those places.
Identifying which energy force dominates, dark matter or dark energy, will give scientists more confidence about whether a big chill or a big rip will be our fate. The best evidence shows dark energy as the driving force, but by how much? Solving this mystery depends on astronomers finding ways to measure how fast the universe is moving. On Earth, it's simple to determine how fast something moves. An airplane, for example, is relatively close. We can look at it and calculate its speed by estimating the distance it travels and timing how long it takes to get from one point to another. But a star's light can travel for millions or billions of years before it can be seen on Earth. By the time its light gets here, the star will be long gone, and it's too far away to gauge its speed or distance traveled with any certainty. The universe is expanding, only scientists cannot give precise answers about how fast. The mystery moves closer to being solved by imaging the cosmos with greater precision. Clearer images from space make it easier to estimate the rate of expansion.
If the universe continues to expand with time, then ultimately all of the energy sources, the nuclear furnaces and stars, would run out and die, and the universe would actually get very cold, and there'd be something called a big chill.
In the big chill scenario, Earth could become a lonely, cold planet as the universe expands. Distances between stars grow so vast that they nearly disappear from view. Over time, they burn out, and eventually the entire universe ends in a frozen state. This sphere demonstrates the principles behind a big chill. The marbles coming out of the sphere are like stars that were formed following the Big Bang. Dark energy propels the stars outward. Dark matter slows them down. In a big chill, the expansion would continue, but the nuclear fuel that causes the stars to burn will eventually run out. From Earth's perspective, the first thing to go would be sunlight. The sun dims as it exhausts its last bits of nuclear fuel. Earth would freeze and become lifeless. And billions of years after humans are gone, the cosmos expands out of view. A few newer stars might remain, but most would have long moved away. The furnace powering the universe burns out. The darkened universe continues to expand, a frozen and lifeless remnant of its once vibrant existence.
Eventually, if this keeps going, if nothing changes in the composition of this energy density, the universe will continue to expand forever. It's going to get colder and colder, and eventually even our neighboring galaxies will be receding from us so fast that we won't be able to see them. So the universe is going to get cold and dark, and it will be a very lonely place.
Astronomers have much to learn about the influence of dark energy and dark matter. And much of the newest information is coming from this probe in deep space. It's sending back information that's helping scientists to interpret the history and the fate of the universe. The night sky, by all appearance, is a quiet and peaceful place. But in reality, there are forces that are driving it to an end. Big science moves astronomers closer to deciphering the universe's great mysteries, including its ultimate fate. The solution to the universe's riddle may well be hidden in this multicolored image. What's incredible is that it's a map of the early universe from the moment it was conceived. And even more fantastic, it reveals a great story that helps cosmologists predict how it will end. The machine that captured this is called WMAP, a NASA satellite that's working around the clock to chart the cosmos.
What we're looking at here is the edge of the visible universe. It's the light that WMAP measured, it's the remnant heat from the Big Bang, and this is literally the oldest light in the universe that we can see. This fossil relic from the early universe tells us a great deal about what the composition of matter was like, what the expansion rate was like, and really what the conditions were at the birth of our universe.
WMAP is one of the great astronomical breakthroughs of the 21st century. Nothing before could give us such a clear image of the energy left over from the Big Bang, energy that scientists call the cosmic microwave background. WMAP is measuring temperature differences in the cosmic microwave background, which may finally make it possible to predict which force will dominate the universe and how that force will bring the cosmos to its end.
The blue spots are regions in the microwave light that was produced by the Big Bang that are slightly colder than the average temperature, and the red spots are regions that are slightly hotter than the average.
Temperature differences revealed by WMAP tell scientists about the nature of the matter and energy that is contained within the universe. They're able to analyze the light patterns and find clues not only about the substance, but also the fate of the universe.
We only capture a tiny part of the electromagnetic spectrum with our eyes, and we have to go to much longer wavelengths. The same wavelengths that are used to heat water in a microwave oven are what we're measuring here with WMAP.
WMAP is so precise that it can detect differences in temperatures as small as 1/1000th of a degree. This sensitivity helps scientists to calculate the ratio of dark matter to dark energy, forces that will determine how the universe ends.
We assembled all those difference measurements and make a map of what the variations look like. And by turning up the contrast, we can basically subtract off this uniform glow from the Big Bang and look for variation.
It doesn't look like much until Gary Hinshaw adjusts the contrast. Then the WMAP image comes to life. Looking at WMAP imagery is in essence taking a journey back through space and time so that we might get some new ideas on the fate of the universe. Pulling away from the probe, and following the path of the light it is collecting, we pass Mars, Jupiter, and Saturn, whose reflected light takes over an hour to reach Earth. Then, leaving the Milky Way, we pass Andromeda, the next nearest galaxy, whose light takes 2.3 million years to reach us, which means we have traveled 2.3 million years back in time. And finally, we arrive back 13 billion years ago, at the beginning of visible light. Before that, superheated hydrogen gas is everywhere. WMAP can see this far back in history. It's confirming important facts about the universe and what's driving it to its demise. The final act for the universe becomes more easily predicted thanks to WMAP. Its information, combined with the work of astronomers, has led to some astounding discoveries concerning a rapidly expanding universe. Rapid expansion supports the dark energy theory and the possibility of a big chill or big rip.
We now know from all the data we've had in the last 10 years that there's, by a factor of 2 to 1, more dark energy than dark matter. So dark energy is the dominant constituent of energy in the universe.
The evidence seems clear. Dark energy is taking over and is leading astronomers into new thoughts about the beginning and the end of the universe.
Before the discovery of dark energy, things were a lot simpler. If we could determine the amount of matter in the universe, then we could say something about its ultimate destiny.
Those simple days are gone, but the proof is adding up and supports the idea that the universe will continue to expand. But will it do so to oblivion?
We've made huge strides over the last century in learning something about the evolution of the universe and its expansion. But we've now raised more questions in some sense than we've been able to answer. And so I think the next decade is going to be even more exciting.
Astronomers have tons and tons of challenges that have been thrown our way by theorists, and we are rapidly trying to figure out how to answer all of these questions. And I think that's the exciting future, because if you can go out and really observe something, you're testing it. And that's what science is all about.
The battle between dark matter and dark energy is expected to go on for billions of years, and humans will be long gone from Earth when the final outcome occurs. But no pursuit has been more significant to science than understanding how the universe arrived, how it works, and how it will end.
It's a never-ending quest. It's driving astronomy. What are the answers to these profound questions? The constituents of the universe, the nature of dark matter, and perhaps the biggest mystery of all, what is the ultimate fate of the universe?